Dr. Sungwon. He studied life science at Seoul University and did Ph.D. in neuroscience at Washington University. After the graduation, he has developed several biological products at Hana Chemical Corporation, and he is currently working at ABLBio. And she is going to talk about some challenges in CNS drug development as a possible collaborative research topic after brief introduction of ABL301. Thank you.
Thank you for the introduction. I'm going to briefly introduce our company and ABL301, the project I'm in charge of. And then I'm going to talk about the challenges I've experienced during development of CNS-related drug, hoping that the IMI collaboration would help for the future and current development of CNS-related drug development in Korea. ABLBio is a pretty new company. It was founded in 2016, February, with only 12 people, and now it grew up with 60 people total, including 48 researchers. And especially, the ABLBio has completed the IPO last year in Korean stock market after successful 3 rounds of series funding. And we are focusing on the development of immuno-oncology and CNS neurodegenerative drugs with our proprietary bispecific antibody technology. We are a small biotech, but we want to be a new trend leader by focusing on the right business domain for the immuno-oncology and neurodegenerative diseases with high unmet needs. And with strong platform technology of bispecific antibody, we have diverse pipelines covering immuno-oncology areas, as well as the BBB platform technology, which increases the BBB penetration of therapeutic antibody. And also, we want rapid growth and high return with minimal risk by trying to out-license our drugs in early stage, as well as we are very open and flexible, and so we have various collaborations with academia and industries in order to accelerate the drug development speed. And here I'm going to talk about the ABL301. ABL301 is basically a bispecific antibody targeting the Parkinson's disease. It is composed of anti-alpha-synuclein IgG and loaded with a BBB shuttle, which is another antibody targeting a target X, which is a receptor expressed on the brain endothelial cell. The alpha-synuclein part targets especially the aggregated form of alpha-synuclein. So alpha-synuclein is expressed basically in normal brains and blood. So if your antibody targets both monomers with normal function and the aggregated form, which is related to the disease, your antibody would lose to go to the right target. And so our ABL301 preferentially targets the aggregated form of the alpha-synuclein, not targeting the monomer. And also, its mechanism of action are mainly 3, and one is ABL301 facilitates the clearing of the extracellular alpha-synuclein. It kind of facilitates the phagocytosis of the extracellular alpha-synuclein by acting through the microglia, which is known to be a scavenger cell inside the brain. And it is known that the alpha-synuclein is acting like a prion, so it travels from one cell to the other cells like infection. And we confirmed that ABL301 inhibits this cell-to-cell transmission of harmful alpha-synuclein. And of course, with the BBB shuttle, this ABL301 has been proven to penetrate the brains in animals better than just mono alpha-synuclein antibody. So with these three main mechanisms of action, we believe that ABL301 has a better target reach inside the brain compared to the competitor molecule, leading to the better efficacy. And here I'm going to talk about the alpha-synuclein a little bit further. Alpha-synuclein is a monomer. Monomer is highly expressed in normal brains and blood, as I mentioned. It's basically 15 kilodalton globular protein, and its main function is known to regulate the neurotransmitter release inside the brain. So you don't want to mess up with the normal protein by acting the antibody. And also, the alpha-synuclein aggregates are thought to be the main culprit of the disease. When you see the post-mortem brain of Parkinson's disease patients, you may see a lot of dense core structure called Lewy body, which is a protein and lipid aggregate, and its main component is alpha-synuclein. So it may be very critical to target the aggregate inside the brain, not the monomer. And also in the dish and animal models, alpha-synuclein aggregates are proven to be toxic, not monomers. So again, it is very critical to selectively targeting the alpha-synuclein aggregate, not the monomer. And our lead alpha-synuclein IgG antibody, clone F, showed clear preference to aggregate. This is the dark blood data showing the interaction of our lead antibody to the aggregates versus monomers. And F and O show the different types of aggregates, and M means monomer. And in contrary to the competitor molecule in clinical phase 2 by Roche, our clone F preferentially recognized the two types of aggregate shown in this signal with serial dilution of protein. And this is sort of analytical data using BIACore, the instrument called BIACore. And our clone F shows the preferential binding, shown as this curve, to the one type of aggregate called fibrils, not the monomer. And when you see this immunostaining data, this data was made using transgenic animals, which means that this transgenic mouse overexpresses the human alpha-synuclein inside its body under the promoter of mouse DAI1. And this mouse brain shows extensive expression of human alpha-synuclein throughout the brain. And when you treat this, our clone F or IgG as a negative control for 3 months, inside this mouse brain, you can see the reduction. Oh, I don't know. You can see the clear reduction of. Thank you. Clear reduction of alpha-synuclein staining, it is especially the aggregated form of alpha-synuclein compared to the IgG control in cortex and hippocampus, which are two major brain areas. And also when you see the expression of GFAP, which is a marker for the astrogliosis, in other words, the marker for neuroinflammation, you can see our clone F treated animals show much less staining than the negative control. It indicates that our clone F reduced the neuroinflammation as well as the accumulation of aggregated form of alpha-synuclein. And because of the limitation of time, I didn't show you the data, but clone F also inhibited the neurodegeneration inside this brain. And also, we had a chance to collaborate with a researcher outside of Korea with the post-mortem brain staining. And our clone F clearly recognized the human Lewy body and Lewy neurites in the postmortem brain tissue with Parkinson's disease. And I'm going to switch the gear to the BBB part. And the blood-brain barrier is sort of firewall inside the human body and bodies. And it kind of protects the brains from toxic molecules, but it does not recognize the toxic molecules from the drugs, so it expels the drugs outside the brain. And actually 95% of the drugs may not be able to penetrate the BBB. So the BBB is thought to be a major obstacle for developing CNS-related drug. And our bispecific antibody loaded with the BBB shuttles showed clear increased penetration of BBB compared to the alpha-synuclein IgG. With another collaboration, we had a chance to test our bispecific antibodies BBB penetration using in vitro transwell system. Basically, this assay system mimics the human blood-brain barrier using human iPSC. We tested the integrity of this monocellular layer by measuring different markers and put our bispecific antibody or just alpha-synuclein antibody, and after a given amount of time, we measured the amount of antibody inside the bottom chamber. And when you saw the result, our final candidate showed more than 15 times better BBB penetration compared to just alpha-synuclein IgG in vitro. And the amount of BBB penetration was even comparable to the positive control, according to the collaborators' data. And next, we move to the in vivo data. And I'm going to skip the explanation in detail about the structure of different bispecific antibodies. But overall, our bispecific antibodies showed clearly better BBB penetration in terms of the brain and CSF compared to just alpha-synuclein IgG here, shown as a clone-F. And so we tested whether this increased BBB penetration would lead to the better efficacy in animal model. And again, we use the transgenic animal model, which overexpresses the human alpha-synuclein. And when we saw the brain tissues of animals with 3-month treatment, here the bispecific antibody, or just a clone-F, or the NI202 is the competitor molecules, which are now still in clinical phase 2 by Biogen. And you can see clearly in terms of the staining of pro-inflammatory cytokine, here IL-1 beta, the animals treated with the bispecific antibody shows much less staining compared to just IgG or clone-F or competitor molecule. And this is the another test. And here we wanted to quantify the level of alpha-synuclein in brain lysates after just short-term treatment. This test was actually followed by the Biogen patent, so it was just testing the effect of very short-term treatment. When you see the brain alpha-synuclein level measured by ELISA in ABL301 treated animals, the level was much lower than just human clone F treated or IgG treated animals. So this series of tests show that indeed ABL301 or bispecific antibodies with BBB shuttles show better efficacy than just mono alpha-synuclein antibody. The reason why I emphasize the animals a lot is I think that the utilization of transgenic animals or animal model for CNS-related disease is very critical and very challenging in Korea. Oftentimes, a lot of animal models are developed by outside of Korea, especially in case with well-characterized animal models. And it is very expensive, and I tried to import these animals, and the documentation took a lot. So if we could utilize sort of collaboration with through the IMI collaboration, it would be very helpful and efficient way to do research. And also in case of the brain banks, as I mentioned, we need to test whether our antibodies could recognize the protein aggregates inside the diseased brain. And especially in case of Parkinson's disease, it is impossible to test inside Korea with postmortem brain tissues. So it will be very helpful to reach to the brain tissues with diseased brain through this collaboration. And the third thing is, as a very small biotech, sometimes it's very hard to reach out to the faculties, especially very famous ones in US or EU. In case of the one collaboration, it took 1 month for me to get a response from a faculty because she's very famous and didn't take care of my emails. So I had to send multiple emails. So if we could launch this collaboration, maybe for a small biotech, it could reduce the amount of time to reach out the famous or very key opinion leaders in the disease areas. So active collaboration with international institutions and universities is vital for time saving and efficient way for a biotech like small biotech like us, especially in case of CNS disease area. So that's all, and thank you.
Thank you for your presentation. You raised some very critical and important research area that need to be solved by some kind of international collaboration. And now we have some Q&A.
So when you say collaboration, does that mean that sharing the profits, or you just looking for the fee for service?
I think it depends, but basically ABLBio kind of pursues fee for service research, but sometimes in my experience, some type of collaboration is more than just fee for service. So actually I learned a lot from the collaboration. Some faculties really indeed willing to share his or her opinion about the results, and it's very helpful to make the project further. And that's one of my hopes actually for if we could have some collaborations.
Any additional question? Okay, thank you for presentation.